Alright, picture this. You're standing in the middle of a lush green forest. Sunlight dapples through the leaves, creating a mosaic of light and shadow on the forest floor. The air is still and calm, carrying the scent of damp earth and pine. The air feels cleaner, right? Almost like you can taste the freshness. That's because forests are nature's ultimate carbon vacuum cleaners. They're constantly working to scrub the air clean, absorbing carbon dioxide and releasing the oxygen we need to breathe. It's a truly remarkable process. But have you ever wondered exactly these trees actually remove carbon dioxide from the atmosphere? What's the mechanism behind this natural wonder? That's where mathematics, and especially differentiation, comes in. It provides us with the tools to understand and quantify these natural processes. Stay with me, because I'm going to show you a super cool way to calculate how quickly a forest locks away carbon. We'll break down the process step by step, making it easy to understand. Let's start with a simple idea. Think of a single tree standing tall and proud. Trees absorb carbon as they grow, using it to build their trunks, branches, and leaves. It's like they're taking carbon out of the air and turning it into wood. And the total amount of carbon stored in a forest over time can be modeled as a function, a mathematical representation of this natural process. Let's call it CT, where T stands for time, like years. This function, CT, will tell us how much carbon is stored in the forest at any given time. Now, the crucial question is, what's the rate at which the forest is capturing carbon at any moment? How quickly is the forest pulling carbon dioxide from the atmosphere? That's the derivative of CT with respect to time. It tells us the instantaneous rate of change of carbon storage. In math speak, that's dc/dt. It's a shorthand way of representing the rate of change of carbon storage with respect to time. Here's a straightforward formulation, a simple equation to illustrate this concept. If CT equals sign kxt2, where k is a constant depending on the type of forest and its conditions, reflecting factors like tree species, climate, and soil quality, then dc/dt equals sign 2kxt. This equation tells us that the rate of carbon capture increases linearly with time. That means as time goes on, the forest is actually capturing carbon faster and faster, at least until it matures. This accelerating rate of carbon capture is a key benefit of forest growth. Let's make it interactive. Imagine a young forest, a collection of saplings reaching for the sky. At year 1, the rate is 2kx1 equals sign 2k, not too shabby. Even in its early stages, the forest is actively capturing carbon. But at year 5, the rate is 2kx5 equals sign 10k. The carbon capture rate has increased significantly. Boom, a 5-fold increase. That's the power of exponential growth in action. This is why planting young forests today pays off big time in the future. It's an investment in a cleaner, healthier planet. So if you ever hear someone talk about carbon sequestration rate, just remember, it's a measure of how effectively a forest is removing carbon dioxide from the atmosphere. It's all about how quickly that CT is changing. The faster CT changes, the more carbon the forest is capturing. Differentiation helps us measure that exact speed. It provides a precise tool for quantifying the carbon sequestration process. Next time you walk through a forest, take a second and think about the incredible mathematical processes at play. Math isn't just about numbers on a page, it's literally in the air you breathe. It's woven into the fabric of the natural world. If you want to see how integration flips this story around, allowing us to calculate the amount of carbon stored, let me know down in the comments. Stay curious and keep growing, just like the trees. Embrace the beauty and complexity of the world around you.